we should start.
All right, great. Everyone, thanks for coming. It's my pleasure to welcome Professor Lindley Winslow from MIT. Lindley leads a group studying fundamental nuclear and particle physics using precision measurements, in particular neutrinoless double beta decay and the search for axions. Today, you will learn more about her work using quantum sensing and quantum measurement to search for the axion, which is a proposed fundamental particle to explain some major open questions in physics, like why the strong nuclear force apparently doesn't violate some symmetries that it probably should, and it's also a potential candidate for dark matter. Those of us in the precision measurement field are very impressed and excited by this work, because one of the big goals in the field is to start implementing and using quantum sensing and quantum measurement to do fundamental physics searches, and Lindley's pioneering work has really paved the way for that to move forward. Lindley received her bachelor's and PhD from Berkeley, and then did a postdoctoral fellowship at MIT before moving to UCLA as a faculty member, and then joining MIT, the faculty at MIT in 2015. She's been awarded, among other things, the L'Oreal for Women in Science Fellowship, a Breakthrough Prize, and an APS Fellowship. Please join me in welcoming Lindley.
Whoops, sorry, Nick. So thank you all for having me here this afternoon. This is my first colloquium in like 3 years, 4 years. So I'm really excited to be here. Let me click on here. So as Nick gave you an introductory, as I start these talks, I used to like to remind people who I am and why you want to listen to me. So what my group searches for is axion dark matter and neutrinos level beta decay. This is also an opportunity to say I used to have a talk that tried to convince everyone that it made complete sense to search for these things because they both had to do with new gut scale physics, not just because I like instrumentation. So that's a great talk. I can come and give it another time. So building on that idea, I am a nuclear or particle experimentalist, depending on the day of the week. And so my lab is interested in sort of novel photodetectors, both warm and cold, quantum dots, crystals of both little and large size, magnets and dilution refrigerators. And these are the tools in our toolbox to go after physics, of which I'll tell you about one particular application today. And so what motivates my work are like the big questions about the universe. And so the two that I am most focused on are what is dark matter? What is the particle nature of dark matter is another way to say that. And why is there more matter than antimatter? And so that gets you back to the two big things that we're looking for. And so in this talk, I wasn't going to go through the full explanation of dark matter and why we think the universe has it. I just wanted to show this picture looking out into space. I had to update the picture. I used to just show the Hubble Deep Field, and now I'm grabbing this one because this one, you actually can see the dark matter there. It's out there sculpting the galaxies. It's causing the gravitational lensing you see. And so we know there's dark matter out there. And the big question is, what is it? Can we explain what it is partically? This also goes to the other big question I'm interested in. What you see out there is matter, not antimatter. And so that is why also I'm looking for neutrinos double beta decay. But today we're going to focus on this question of axion dark matter. So the other reason I'm up here speaking with you today is I spent the last 2 years as one of the conveners of the SNOMAS community process that was trying to organize high energy physics. And specifically, I was responsible for wave-like dark matter. And so what I hear from a lot of people is that direct dark matter searches can feel like a zoo where everyone has their favorite detector, an animal, and each of these animals seems to be carrying a balloon. And so for me, the balloon is some sort of new technique, often quantum based, that makes the detector special, better to look for some particular dark matter candidate. So if you're feeling like you're at a zoo in some dark matter talks, that might not be wrong, but I would like to try to explain to you all today why axion dark matter specifically actually requires a suite of experiments and why it might feel a little bit different than what you're used to in a particle experiment talk, where we're talking about one detector that can make either the ultimate measurement or is a multi-purpose detector that goes after many things. And so that's what I'm going to try to convince you today, and why I think why I'm standing up here. And so you can tell me afterwards if I've convinced you, okay? This is the job. I'm putting the audience to work. So then the goals for the talk: describe the suite of experiments that are going to be needed for a definitive search for the axion. Can we actually rule out all of the parameter space or make a discovery? I really am hoping for a discovery of dark matter, of axion dark matter in the parameter space of interest. Understand how this relates to different regimes of quantum sensing, of which I know I have a lot of experts in the audience. And what I would like to do is try to connect an axion discovery to other key questions in particle and nuclear physics. So these are my goals. And so then after that, I wanted to tell you about what we do specifically in my lab, which is Abracadabra 10 centimeter, and now its expansion with the DMRadio program. So as I warned, this is a new talk, and you have a job at the end is to tell me if I convinced you about this suite of experiments and that axion dark matter is very exciting. So axion dark matter fits in this general category of wave-like dark matter candidates. And so the definition of wave-like dark matter is dark matter particles with masses less than 1 eV. And a little bit later, I'll try to give you a little bit more reason of why that 1 eV is really critical. So it falls into broad classifications of categories, broad candidate categories, that's really hard to say, which are based on their CP properties. CP, the symmetry, is sort of the mirror-like symmetry that we believe the universe should follow some of the time in particle physics. And so you have candidates that are pseudoscalars under CP, scalars, or vectors. The general production mechanism in the universe is this athermal production. And so what do I mean by that? Most of the dark matter candidates you're familiar with are thermally coupled with the universe at early times, and therefore they're very much tied to the thermal evolution of the universe. And then you're very constrained as to what you can do with your dark matter candidates. As soon as you have an athermal production, you just make them in the early universe and they stay there. And that's a very simple, oversimplified way to say it, but that's how you can understand why something so like could be a dark matter candidate. And so this is just generally true of these wave-like dark matter candidates. And so finally, for the detection principle, you have a wave-like candidate. And so what you're going to look for is the coherent interaction of your wave with your detector. And so for this broad category that, once again, I admit can feel like a zoo of these wave-like dark matter candidates, there is some organizing principle behind what we're looking for. It's not disorganized. So the most famous candidate in this group is the QCD axion. And so what is the QCD axion? So in very particle physics terms, we have this problem with the strong interaction that we expect it to violate the CP symmetry, this mirror-like symmetry. The standard model of particle physics says the strong interaction should violate CP symmetry, yet it doesn't. And so we need a reason that the strong interaction doesn't violate CP symmetry. So we add a new symmetry, a U1PQ symmetry to the standard model, and this breaks and you make these axion particles. And this was the excitement of the early 80s with Pache and Quinn coming up with this new symmetry, and then Frank Wilczek actually realizing that it made particles that could be good dark matter particles. So if you have this particle that's made by the breaking of the symmetry in the early universe, how do you actually detect it? Well, it's going to couple to photons, nucleons, and electrons. And you end up with, once again, two broad categories of models. One broad candidate of models that can solve both this strong CP and be dark matter is what we call KSDZ, which would introduce new heavy quarks into the standard model. And another broad category of particles, DFSZ. These are all people's names. They aren't the same people's names, even though there's some repeated letters. And this category of models adds additional Higgs fields. And so the second takeaway from why we love QCD axions is they solve a problem with the strong interaction. They can be dark matter. And if you discover them, you will have evidence of new physics that we may be able to reach at an accelerator. And I promise as soon as we have an axion discovery, we will have lots and lots of papers about what we could see at a collider. I'd be willing to take bets on that. And so that's why people love the QCD axion, because it unites so many issues in particle physics. So what you see up on that plot there is the classic plot that every axion talk will show you, which is the mass of the axion on the x-axis, and it's usually the coupling to photons on the y-axis. And you see this yellow band through the center that goes on a diagonal. That is the QCD axion band. That is the sort of parameter space for these models where the QCD axion can be dark matter and it can solve the strong CP problem, the strong CP problem. So you're going to see this plot a lot. So stop me here if you didn't get that. So mass on the x-axis, coupling, usually coupling to photons on the y-axis, and the QCD axion always falls on this band in the center. One of the things about the theory of QCD axions, it doesn't actually specify the mass of the axion. And so, what is, 12, 13, 15 orders of magnitude of mass among friends? So there's where you get the first challenge of this wave-like dark matter, is that you are not usually guided to where in the parameter space that you're looking for. So that's going to be the challenge. So I talked a lot about the QCD axion and why we love the QCD axion. So there are these things called ALPS, which are axion-like particles. These are particles that don't solve the strong CP problem, but are still produced in a similar mechanism. And we like ALPS because, well, the parameter space for them is easier to reach. And we'll talk about that a little bit more. But they're made in a lot of higher order theories, string-like theories. It's like hard not to make axion-like particles. And so I'm not a theorist, but this is what my theory friends tell me. And so in between, one of the things that'll be very exciting to discover the QCD, discover an axion, is we'll actually be disentangling whether we actually saw a QCD axion or whether we saw one of these ALPS. And so once again, why are we excited to do these experiments? Is that we have a broad range of things that we can look for, especially if we have a discovery. Excellent. So QCD axions, ALPS, lots of axions. So that's what we're looking for. And I'm an experimentalist. So the next question is, how do we actually go about detecting these particles? How do we build a detector? So where we need to start is that we're looking for wave-like dark matter. And so much of what we do as particle physicists is look for particles. And so the first thing you have to do is you have to stop thinking about particles like heavy dark matter, like WIMPs that you see on the left, and you have to start thinking in terms of waves. And so axions are not even like little particles like you see there. They're actually so small that you've actually crossed into the regime of actually being a wave. You have to talk about a field that we're in and a wave that you are trying to detect. So fundamentally, you're going to have very different detection techniques than normal particle physics experiments. And so what are the numbers that go along with that? And so I think this is where I'm trying to build some intuition of why is this wave-like dark matter? Why is this 1 eV sort of realm special? And so what you need to do is actually you can calculate the de Broglie wavelength of an axion versus a WIMP. So you can put in what is a nano eV axion at 10 eV. And what you end up with is a wavelength of 10,000 kilometers. So this thing is not localized in our lab. It's not wandering in. You're talking about scales of the order of the spectrum. And so this is really, it's really wave-like. And occupancy numbers of like 10 to the 44. Versus like you can put in for what a 100 GeV WIMP, sort of the classic particle dark matter would be, and the wavelength is 10 to the minus 16 kilometers. So that's something that's very particle-like, and the occupancy of like 10 to the minus 36. So now you understand like why we call this wave-like dark matter down here. We're really dealing with these very, very wave-like things. Cool. So if you're detecting a wave, are you actually looking for something like recoiling particles? No, you're going to actually have to measure frequency. So what falls out of the axion mechanism, or sorry, when I say axions, I mean ALPS and QCD axion, is that the universe is filled with this field, A of t, axion, that oscillates with a frequency corresponding to the mass of the axion. So all around us, if there's an axion field, we don't know its mass, but there is this propagating field all around us. And so if you couple that into your detector, you're going to measure the frequency of the wave in your detector. And what you're looking for is above the noise of your experiment, a very narrow band, because you have a particle that is oscillating at exactly its mass. And so the narrowness of that is about 1 part in a million. And so that's the signal that you're looking for. So experimentally, it's very clean. As soon as you can find it, of course, we don't know the exact frequency, and that's one of the difficulties, but you know what you're looking for. And it's actually, nature has been even more kind to us because the shape of that line has a very distinctive shape due to the velocity distribution of dark matter in the halo. So it's not that we just have to find a very narrow line. This line should indicate that it is dark matter because it will have the velocity distribution that we expect in the halo. We're going to need a suite of experiments depending on the wavelength of the photons, because now we're going to look for photons. And now, what are the detectors that you would build? So you're measuring photons. It is F mu nu. You all saw it up there. So what we're doing is we're modifying Maxwell's equation. And at one of my coffees earlier, had a delightful first year, and she was very excited because she knew about Maxwell's equations. And so this is what we're doing. We're modifying Maxwell's equations for the axion. And you'll see terms that are proportional to the gradient in the axion field. Those will be small. And so really what we're going to focus on there is Ampere's law and modifications of Ampere's law. So you have different wavelengths. You're going to be in different regimes for understanding the physics of Ampere's law. And so the regime that is easiest to understand is this so-called quasi-static regime, where your wavelength of your wavelength dark matter is much, much larger than your experiment. And so you have effective currents. And so this is freshman, sophomore level E&M. Right-hand rule, it's very useful. We'll do some right-hand rule later. In the regime where the wavelength of your dark matter is proportional to the size of your experiment, you're in the cavity regime. And this is where many of the Axion experiments to date have lived. This is some advanced sort of junior level Griffith E&M to calculate the modes of the cavity that you're exciting. It can get a little bit messier, but you know that's the level. And then finally, if the wavelength of your dark matter is much smaller than the size of your experiment, you'll actually be in the radiation regime where you're forcing the axion to convert to real photons. This is where you build the we'll talk about that in a second. This is some very nasty graduate level, and maybe even worse E&M to calculate. Okay, so experiments now are trying to work in all of these regimes. And so quasi-static regime, this is my own experiment, and you're going to hear a lot more about Abracadabra in a minute. And so effective currents, and to go from there. The cavity regime is so-called because it's a cavity. You're looking for your wave-like dark matter, your axion, in the presence of a high magnetic field. So you put the cavity in a high magnetic field to excite the cavity. You can tune the cavity to different frequencies with a tuning rod, and you will look for your axion signal in the readout of the cavity. And so the most famous experiment is ADMX, which you see on the right, and a smaller, higher frequency experiment on the left, Haystack, which runs at Yale. And so then finally, you have this radiation regime for the highest mass axions. They're still in the wave-like regime. And these are the so-called dielectric haloscopes, where you use the boundary conditions at the interface of the dielectric to force the conversion in this high magnetic field. And these are ideas like MEDMAX and BRED at Fermilab that are trying to make this. And here, people argue a lot about, did they actually do the calculations correctly? Because as I told you, these are some very hard calculations on how this works. So where are we? So this is all of the gory details of the state of axion physics. And so as I promised you, on the x-axis, you have the mass of the axion. On the y-axis, you have the coupling to photons. And you see that diagonal line for the QCD axion. And you will see some red lines coming down, which are the current cavity experiments. And you'll see that they are now beginning to turn into the axion, which is very exciting. There's a lot of limits coming in green from very astrophysical sources and some other technologies, the so-called helioscopes for looking for interactions in the sun that are there. And so that's the current status of things. And so what I would like to do is try to simplify that, because that's very hard to look at, even for me. So let's try something a little simpler, and let me close this on the right. I didn't realize that was projecting. Okay, so here is sort of imposing the different detector techniques onto that GA gamma gamma plot. Sorry, it's getting cut off on the right. So on the x-axis, you have the mass of the axion, and on the left, you just have no axis. And so where did the experiments fall? And so at the top, you have the bounds coming from black holes. On the right, you have the bounds coming from astrophysics. At low mass, you have the quasi-static regime. In the middle, you have the cavity regime. And at high masses, above about 10 to the minus 4 eV, you have the radiation regime. So at the time of about a decade ago, there was no one that was probing the QCD axion anywhere in this plot. So now today, as we sort of do this, we're in the middle of this decadal plan for particle physics. You have the beginning of exploring the cavity regime for the QCD axion, and we haven't gotten very far. So you have ADMXG2 running, and you have the experiments Haystack at Yale and CAP in Korea that are beginning to go down into this band. And so what are we proposing now? Well, there's two experiments that are on deck, my own DMRadio meter cube and ADMX-EFR, which are waiting for money to flow. And they're going to try to carve out the space that you see there. And what we're looking for is now, how do you cover that full band? And so what are you going to need? And so to cover this full band, you're going to need cryogenic infrastructure. If you can't tell, we are making, these are hard measurements, otherwise it wouldn't, everyone would have done it already. You're going to need large and or high field magnets because the axion needs to convert in a high magnetic field. You're going to need high Q good cavities to try to do this amplification. And once you get the signal out of your detector, you're going to want that signal not to be destroyed by noise. And so you're going to want to push beyond the standard quantum limit in your readout to see this signal. And so those are the ingredients of the axion field: is big magnets, high Q cavities, and BSQL readout. And it's the geometry that you're going to need to change, and of course, the details of that readout to make these measurements. So just a little bit about the BSQL, beyond the standard quantum limit readout. And sorry, this slide is getting cut off. I think the important take-home point that I would like, and I alluded to it at the beginning with the balloons for each experiment, is that when you're talking about the readout and pushing beyond the standard quantum limit, pushing your noise as low as possible, that's going to be frequency dependent too. So the BSQL that works for nano EV axions is not going to be the same standard beyond the standard quantum limit you need at the micro EV readout, and especially not in that so-called dielectric haloscopes, that high mass axion. So what this is all going towards, and there's ideas though in all of these areas. So if you felt like there was a zoo, that is why, is that you have multiple different, very distinct bands where you're going to need different detector geometry. And within those bands, you can have different BSQL readout to really push your noise and get the biggest, most sensitive signal that you can get out of your detector. And so there are lots of ideas of how to do that. And we are still at the point of, if you're not the two that are on deck trying to build sort of flagship experiments, of sort of doing the demonstrators, doing the Pathfinder experiment to see which geometry with which BSQL readout will get you down to the QCD axion. And so that is why it feels like a zoo, and why, though, eventually we are going to need a suite of experiments. So I have a prediction and a summary just for this part of the talk. So we have these two cosmologies: the pre-inflation scenario below 1 micro EV, the post-inflation above a micro EV, roughly 3 frequency regimes, and roughly 3 noise regimes for the BSQL readout. And so my guess is it's going to take about 5 experiments to do this. And so 2 of them are waiting, and I think it's going to take another 3 to actually fully cover the bandwidth. And so that's what we're looking for axions and what the field needs to do. And so once again, it looks very different than the one experiment that will do it all. So what would be the consequence of discovery? So I have like a couple scenarios so you get a flavor for what would happen. So the black star there on this bound shows a possible QCD axion discovery. This would be in the regime firmly after inflation. So you would know that the axion was made after inflation because that's where its mass is. If it's at DFSZ, if it's in the QCD axion band, it means that you've expanded the Higgs sector or you have additional quarks. And once again, that's going to have consequences for the colliders that you would build. And what you would need to do is you would then need to test the nuclear and electron couplings of the axion to see if you really have an axion or you have an axion-like particle. And then you would look at the shape of the line to tell you, do we live in a stream in the halo? You know, what is our halo structure? And so you'd have lots of fun actually doing that axion cosmology. Axion astrophysics. So that's what happens if you make a discovery there. If you make a discovery down here, in my favorite sort of regime, oops, I shouldn't have given that away. This is a QCD axion down here that would be made after inflation. So now you know that the axion was present during inflation. This mass range corresponds to a gut scale axion. So you would have axion new physics at the gut scale where we really think we should have some new physics. There are consequences here for CMB signatures because you have another field during inflation. And once again, though, what you would need to do is test the nuclear and electron couplings, and you would do the line shapes and actually see what your halo is looking like. So that is the consequences for that one. And so then the scenario I particularly like, because we had hit it before any others, is what if we make a discovery here? So this is an axion-like particle. This is not the QCD axion, and it would be an instantaneous proof of some sort of higher order theory. You would have something that is not just Higgs and not just quarks added. And so this would have consequences for signatures in accelerator-based experiments too. And once again, though, you would want to test the nuclear and electron couplings because you would want to see what this thing is doing. And you could still do this line shape and explore your halo. And so no matter where the axion is discovered, you would have consequences for the rest of particle physics. And so I think, you know, putting this all together, big magnets, BSQL readout, and the consequences is why you're seeing this growth in this community. So this is the number of abstracts at April meeting, and you'll notice if you could see all the way over to the right that axions now overwhelm WIMP abstracts. And then why so many people as part of this decadal planning were really interested in being part of this growing axion community. So that is my advertisement for axions more generally, and why you're beginning to hear about them so much. Why they've had this resurgence since they're first being theorized in the early 80s, and why I'm particularly excited. And so now I'm going to tell you about the work in my own lab, which is Abracadabra, and then our transition into the DMRadio program. So Abracadabra, actually I should pause. It does stand for something. I need to thank my colleague Jesse Thaler, who is a Scrabble champion. Yes. So Abracadabra is a broadband / resonant approach to cosmic axion detection with an amplifying B field ring apparatus. So it's telling you what we're doing. And so what are we looking for? So once again, this is this classic axion parameter space, axion mass, axion coupling. What Abracadabra is looking for is we're in this long wavelength light mass regime. I'm particularly interested in that nano EV gut scale axion, because all the rest of my program is also looking for gut scale things. And that's what I would have told you in the other talk. And so this is where we want to look. And so how do you build an experiment in this regime? And so this is the PDG plot from before the running of Abracadabra. And so you'll notice that there are no direct, so those are the green lines, those are the haloscopes, the cavity-based experiments. There are no direct searches for axions in this regime before Abracadabra. So there are solar experiments and various sort of light shining through wall like things. I didn't tell you about that whole class of axion experiments. We can talk about that later. Excellent. And so once again, if you're looking down in this nano EV range, what I'm looking for is that pre-inflation gut scale axion is what I'm interested in. So quasi-static regime, what does that actually mean now for this experiment? So let's talk it through. What is this broadband resonant approach to cosmic axion detecting with a B field ring apparatus? So what is our B field ring apparatus? So this is your B field ring apparatus. You have a toroidal magnet. And so what happens? So this is where I promised you got to do the right-hand rule in colloquium. It'll be interactive. And so this is based on a paper by Yoni Khan, Ben Sapti, and Jesse Thaler. So you have a toroidal magnet with a B field going around it in the donut. The axion couples to the B field. This is Ampere's law. This is the effective current. So the effective current of the axion is running around like this, and it's oscillating with a frequency corresponding to its mass. And so you have an oscillating current in the direction of the B field. And so quite literally, right-hand rule, fingers curl up and around. what it creates is a real magnetic field up to the center of the toroid, where classically there should be no magnetic field. And so as a rare event search experimentalist, this is a beautiful setup because it's a zero background experiment, well, to first order. Because experiment is never that simple as a floating donut in space. And so how do you actually build this experiment? And so this has been the motivation of basically the past 5 to almost 7 years now of working on Abracadabra, is how to find that induced field. And so we know what the signal is. I want to remind you, it's very distinctive. We're looking for a line in frequency space. And so what is it that we need to get started? So the magnet was purchased with an NSF Eager Award. These are awards that you just have to convince your program manager that you have a good idea. So about $80K for the magnet. I already had the dilution refrigerator. I had to buy a squid current sensor. I only had the squid amplifiers. And then you need to do some sort of vibration isolation because a shaking magnetic field looks like an axion. And then some warm and cold EM shielding. And so that's Abracadabra. Could we put it all together and could we make this experiment work? And that was the big question for Abracadabra. So the fun part, how do you build a toroidal magnet? And so the magnet is assembled from these Delrin supports that you see up on the left. Delrin is also called bakelite. They used to make jewelry out of it. And so you assemble, you glue them together. We assembled it actually in 3 parts and then wound it. And so you see the mechanical support and then the final magnet being loaded into its superconducting shield at the vendor and installed in 2017, and it didn't. So now you improve it, do a better holding of that central pickup loop. So you need a loop to pick up the induced B field and put it in. We also at that point suspended the whole thing from a Kevlar string and a spring. And so the whole experiment is hanging from a piece of Kevlar that is thin enough that you don't see it actually hanging down through the dilution refrigerator. And so this is just to keep the magnet from shaking. And so those were the 2 big improvements to make this thing work. And so this is the setup for those that like to see inside detectors. You have the magnet inside its superconducting shield at the bottom of the dilution refrigerator. And in this run, we had the squids up at the 700 mK plate. And then you can see some of the thermalization of the mat on the right and the mixing chamber plate. So it is not very complicated as long as you have the stuff to cool it all down. And so one of the last big points for doing this is, so you have this magnetic field coming up through a loop and you're looking for frequency. The question is, do you do a broadband search and just see all frequencies of axions at the same time? So that's just taking that pickup loop and coupling it directly into your squid current sensor. Or you could couple the pickup loop through an RLC circuit and get an amplification of the signal if you're on frequency, on resonance, before you put it into a squid. So on the right, so for the resonant readout, you get this enhancement proportional to the Q value, and Q values can be up to 10 to the 6, and this is a classic trick. The problem is then you need to build that resonance circuit. That costs money. If you can't tell, I was on a strict budget. So what we did is we did this broadband readout just to see for the first time, could you put the pieces together and actually get a signal out of this thing. The nice thing about doing a broadband readout is that you also see all of the frequencies at once. You can look and see what's correlated at low frequencies with high frequencies, and it just simplifies everything. What I'm covering up here is that there's been a lot of work by Kent Irwin and Saptarshi Chaudhuri on how do you optimize the coupling of the axion field into this sort of circuit, and how do you optimize the scan strategy if you are using an RLC circuit. And so it's a very complete work. And so as you go forward, there is better ways to do this, but this is really the first, can we make it work experiment. So these are the details of our broadband readout. And of course, you need some magnetic shielding. So the funny story here is that MIT used to run a small LINAC for low energy, for medium energy nuclear physics that's been decommissioned. And so we went and harvested the mu metal shielding. Yes, you can go harvest new metal off of things. And so the first results went on the archive in October 2018. And so I just put these papers, there's a long technical paper with all the details of the experiment. And so I think this is for this audience that's really exciting, which is what is the frequency you read out? And so this is the data that came out of Abracadabra, 10 centimeters. And so on the x-axis, you have frequency. On the y-axis, you have the power of the flux through the pickup loop. And so what you see is two different noise sources. At low frequency, you see this forest of lines, which is the vibrations of the magnet. You can't build a perfect magnet, so there'll be some stray fields, and that will vibrate, especially in a dilution refrigerator, which is cold. And so that looks like an Axion signal. So you see that. So you can't really do an analysis down there. There's too many lines. And at high frequency, we see some inefficiencies, our EM shielding, some weird shapes there. And then in the center, though, you have this region where we actually were able to hit the noise and just see the noise in our squid readout. So that's pretty good for an experiment that was thrown together with harvested EM shielding. So one of the details that is hard, but is not as interesting is how do you calibrate this thing? So we actually had a secondary loop, a calibration loop, where we could inject Axion signals and actually pull out the gain of the detector response. And so actually doing this, taught us a lot about the response of the detector, and also about effects like the fact that if you have two wires next to each other, they have an inductance, and that needs to be part of the gain calculation. But yes, details. And so, though, with that nice clean region, but you can go ahead and do an actual physics search. And so that's what we did. And so we have a test statistic. We look for peaks. We actually compare magnet off data to magnet on data. You need the magnet on to see an axion. And so that allowed us to rule out most of the mass points. But we did a comparison to a template Axion signal over 8 million mass points, and set a 5 sigma discovery threshold to actually set bounds on the Axion. And so this is what we actually were able to find. And so this is the first run. And so with this little tiny experiment, we were approaching these much larger, sort of older helioscope experiments. And so we're very proud of this. So these are the first direct searches for an Axion in the low mass region with this sort of direct technique. So this is the classic plot. On the x-axis, the mass Axion, on the y, the coupling, and you see Abracadabra's first bounds. And what we like to point out is on the right, the bounds for ADMX, this thing is gigantic. On the left, the solar Axion experiment, which is an LHC magnet that moves around. And then my little Abracadabra, which is the size of a pomelo, that was actually fairly competitive. It's not quite a grapefruit. It's a little bigger than a grapefruit. Okay. And so we set up actually right before everything shut down for a third run of Abracadabra. And so instead of using a pickup loop, we did a bunch of simulations for a pickup cylinder to capture more flux. Ideally, you do a whole sheath, but that's hard to engineer how to wrap the whole magnet. And so increase the gain and do another run for Abracadabra. And so this is the data from our most recent result. Published in 2021. And so we were able to improve the limits by a factor of 4 to 10, depending on the frequency space and the noise. In the most interesting parameter space around the nano EV, we finally surpassed the helioscope's CAS limits. Unfortunately, with the increase in gain of the system, we were no longer at the squid noise floor. We actually now fully saw all of the noise in the system, mainly due to the vibration of the magnet. And so that is now in this experiment, the driving limitation. And so you might say, what's next? So before going on, I need to thank my collaborators and the leaders of this third run, which were the experimental graduate student Chiara Salemi and the lead theory student, now postdoc at MIT, Josh Foster, who does general dark matter theory. So then what comes next? I have my pomelo. How do I do a better experiment that's not limited by environmental noise? The answer is you need to design a better experiment. You also need to get bigger. And so now you will recognize this experiment, which the answer is you have to be bigger. And so that's what's next. And so I introduce you to the DMRadio collaboration. I am a spokesperson to Kent Irwin's project director. And so it's combining mainly SLAC, Stanford, Berkeley, and MIT with support from a variety of other smaller efforts. So this is the DMRadio program, the dark matter radio wavelength. You guys get it. Wavelength dark matter radio, your tuning frequency. It makes sense. Okay. And so the goal of this program is a definitive search for axions below 1 microeV. So this is the pre-inflation scenario, some sort of new gut scale physics. So what do we need? We need a bigger magnet. We've hit the limits with what you can do with the Abra size magnet. We're still going to need that dilution refrigerator. We're going to need to move to a resonant readout approach. So if you're really going to do a flagship measurement, you need that advantage that you get by doing the resonant readout with Q values of sort of 10 to the 6. You're still going to, though, need to do some vibration isolation and all this boring stuff of warm and cold shielding to actually be able to see the limits of the readout. And so it's a family of experiments to do this and get us down all the way. So the first in this would be DMRadio 50 liter. So this is just a slightly bigger version of Abracadabra. It's still a toroidal shaped magnet, and it's currently under construction. So the magnet company is in the process of winding that magnet for delivery this summer. And so the goal of this is to continue sort of perfecting our technique to do a better job of vibration isolation. And the end goal of 50 liter, though, is to be a test stand for the VSQL readout. So how do you do VSQL readout in this frequency regime? And so that's what 50 liter is, and good work for us while we wait for the larger experiment, which is DMRadio meter cubed, which you see up at higher frequencies. So it's looking for axions between 5 and 200 megahertz. So if you ask after Abracadabra and 50 liter, what's the natural scale of the experiment? It's something on the order of a meter cubed, of a magnet of that scale. And so if you want to hit the QCD axion band, it goes down on the diagonal. So if you're going to have a bigger magnet, but not a gigantic magnet, you need to go up in frequency. And so that's what DMRadio meter cubed is going to do. And so at a meter cubed, you can reach the DFSC, the QCD axion in this frequency regime. The problem is that at somewhere above 5 megahertz, the quasi-static limit, this limit that allows you just to do your calculations with effective currents, starts breaking down, and you start entering the cavity regime. And so a lot of our work lately has been understanding how do you read out a detector that's entering the quasi-static, which is beginning to exit this quasi-static regime, and you're seeing modes of the cavities. So this is the experiment for a cubic meter. So one of the things we need to do is we have to move away from the toroid magnet because modes start showing up in it earlier. And so we have a big solenoid magnet, and this is what we're going to do. It's a little bit more complicated than the toroid. So solenoid magnet B field going up, you're going to then end up with an effective current oscillating up and down, which will induce an axion field, which is in the axial direction like this. So how do you read out, do a pickup loop to pick out that axial field? You're going to install a coax that looks like this. And so the induced current that's going to show up on this is red. It's going to go around like that. And so you're just going to pick up the signal there and then send that to your readout. And so now all the work is how do you interface this coax structure into the dilution refrigerator, into the cryogenics, interface it with this big solenoid magnet, design a solenoid magnet that doesn't have a lot of field up where your readout is. And so that's what we've been up to. And we're in the process of preparing for a CD2, for those that know such things, like review, and a TDR for later this year. So lots of fun there. And so then as I finish up my talk, that's meter cube. I told you about 50 liter. I told you about meter cube. You see the current bounds for Abracadabra in here. So what is it that I really want to do? What I really want to do is I want to search for that nano EV axion. The 5 to 200 is nice, but I really want to go after that gut scale axion. And so that's DMRadio gut that you see there in pink. And so there is a paper that you can read about what needs to happen, but it's going to take more R&D to do that. So DMRadio gut, and so this is where some in the audience can laugh, is about a 10-meter diameter magnet. So it's about the diameter of the CMS magnet. So we built magnets on that scale, but not at this field. And you're going to, though, need to integrate it with this precision readout. So how do you do that at that scale? And you can't just go to this scale of experiment. So that's why we need to do 50 liter. We need to do, which will actually be a prototype for gut. We need to do meter cubed. And then I guess 15, 20 years, what I want to do is DMRadio gut. And so at that is my dream. The one thing I would note is that the 10-meter scale magnet aligns with what the new fusion company in Massachusetts, Commonwealth Fusion, wants to build. So my goal is for them to build the magnet and then port it over so I can do Axion physics with it. But yes, but that's why I'm realistic. 15 years, maybe 20. And so that I want to thank you all for listening to me, for only laughing a little bit about DMRadio gut, and open for questions.
Thank you, Lindley. If you're here in the audience, you can just raise your hand. If you're on Zoom, you can raise your virtual hand or put something in the chat window, which I will monitor.
I see one question up from the top.
Determine the lower limit for your magnet size if you want it to go larger, but where to start?
The lower limit?
Yeah.
You want as big a magnet as you can, because the strength of your signal is proportional to the magnetic field. And depending on the regime, it's BV or other, some other way. So that's money. And so the Abracadabra money was the biggest, sorry, the Abracadabra magnet was the biggest magnet I could buy, given the amount of money, and that would fit my dilution refrigerator without new shields. Yeah. So yes, this is the interplay of what you have money and what you can build. Yeah. Yeah. All the way in the back.
I saw one line go by on, I think it's slide 67. You didn't mention it out loud, but you said you were trying to avoid the look elsewhere effect. What is the look?
Oh, right. When you are doing a peak search, there's some probability that you will find a peak anywhere, and so you have to do the statistical correction for if I looked here and saw something, and I didn't look over here. What?
Like a statistical feedback?
Yeah. So quite literally, and like for those that do peak searches, the LHC it's the classic question of what you need to do. And so that was me just proving that we know how to do data analysis to my LHC colleagues. But yeah, you have to be careful about that since we don't know the frequency. As soon as we know the frequency, we don't have to do that.
Another idea for detecting nano-EV axions is through the time dependence of electric dipole moments driven by the coherent oscillations of the axion field.
Right.
Do you think that also has noteworthy discovery potential? Is it valuable to do both that? And
so I was sort of trying to make that point that at the very least, you're going to want the other techniques that are coupling to the other couplings of the axion after you see it with photons. I do have a bias because I do come from the nuclear physics community that things are much cleaner if you can do it with photons. And the technical challenges on each of the other couplings, I think, are more difficult than simple scaling of the magnetic field. At some level, we could just do it by scaling the magnetic field, though it's more elegant to get the resonant readout. And maybe that magnet would be just too big. But that's what I would say. Is, some of those, all of those techniques require, just some things that I find a little bit harder, either large amounts of fluoride xenon or what have you.
So you touched a bit on this resonant technique. Since you want to cover, as you mentioned, just a broad range of frequencies, is that something that you just sort of put in one resonator, take a bunch of data, form the thing up, put it in a different resonator, or is there some more clever way of doing it?
So there's some cleverness. I sort of pointed out the Shaduri and Irwin paper that you can scan faster because you still have sensitivity out in the tails of your resonance function. But at some level, you can scan a certain range of frequencies, and you warm up and you plop something else in. And so that's the paper that's like sitting on Slack for me now, which is what is the exact set. We actually have to change the coaxes too. What's the exact set of coaxes with the exact readout for each of these frequency regimes. And so it's looking about like 6 or so to do the 5 to 200 megahertz. Yeah. Oh, Leon, back.
For the DMRadio cut, I mean, you're starting to reach down into acoustic frequencies. And anyone thinking about the acoustic noise of a 10-meter magnet?
Yes.
Yes.
And so like when my Softy, my theory friend Ben Yoni came into my office to try to convince me to do this, I'm like, and they were all worried about very detailed things about like they were loving it at the SQL readout, and I'm like, it's going to be the vibrations, yeah, and so I'm like, yeah, we're going to go see our friends at LIGO. Exactly.
I had a question about, so you said the noise in Abracadabra was limited by the mechanical noise?
Yeah.
And vibration?
That sets our lower frequency bounds, yeah.
Okay, I guess I was wondering how far you were from the quantum limited noise, just like how far you are from like the beyond standard quantum limit, like technically.
So I think the sort of looking at it there, the middle regime and sort of kilohertz up to a couple hundred kilohertz, we actually saw the squid noise floor for the squids we were using. I don't have any, I didn't have the money for more fancy, nor do I think it actually makes sense given the setup, but that is the exact goal of 50 meter, is to improve the vibration isolation, have a bigger magnet, and actually be able to start swapping in different readout techniques. Yeah.
I guess this is kind of a question that gets away from the regime you're interested in maybe, but is there some like unfortunate intermediate regime between wave-like and particle-like dark matter, where it's kind of, you know, for some super early wavelengths where it's kind of not quite obvious how to engineer the experiments and put them on that.
No, you're hitting on a very interesting problem. So obviously I have a love of wave-like dark matter. This is what I spent 2 years coordinating snowmass things for those who do it. And so there are frequency regimes that are harder. And so you ask why we stop at 200 for us, up to ADMX, sorry, up to the green line there. That's a very hard frequency regime because of the frequencies involved. Whether you're using a very big cavity or an LC, so that's one. And so then if you ask me, how do we convert, like there is now reason to go from 1 eV up to the WIMP limits. How do you do that? And so this is where a lot of people are thinking about, you know, some novel materials, direct materials, et cetera. Yes, an idea came across my desk about quantum dots with S and SPDs. You get the idea. And so, yeah, I'm like, I really like that one because my other work involves quantum dots, and then it would be an excuse. Yeah, exactly. And so what I would say is, as you move from 1 eV up to the lower bounds of our current WIMP experiments, for me, what I'm struggling with there is the theoretical motivation. And so you have this back and forth of, is the theory motivation strong enough there? And I hope what I convinced you all here is when you're talking about the QCD Axion, there's a lot of reasons to kind of look there. Each of them individually you might be able to pick apart, and I know people do, but there's a lot of motivation for this sort of this frequency regime that you see up here. And as soon as someone can give me a really good motivation, I think those ideas will come on shell. And so those ideas are all kind of at the same level though where Abracadabra was. Like, can we just put some stuff together for not that much money? And does the idea even work? And so I think that is the level of those, and why, though you're not seeing them on plots for like what we need to do this decade, it's still definitely in Pathfinder mode versus like project mode. But yes, cool. Now I got to opine for a second on dark matter in general.
This entire range and don't find any evidence for axions. What does that imply?
So there's two options. The option I don't like is that axions are like a fraction of the dark matter. So what if they're like 10% and you only scanned up to them being 100%? So what's on that y-axis, and I didn't really go into, this is assuming, DFSZ is assuming that the axions are all of the dark matter. So if they're only 10%, then you need to go down another factor 10 in sensitivity, roughly. And so you just didn't scan deeper. But I think once again, sort of similar to my answer there, is you would need a theoretical motivation of some evidence that the axions are there to justify another round of experiments to go deeper. And so I think that's a second question. But that's one of the things we worry about. Or you just rule out axions, period. And nature just has messy, strong CP, and nature just chose that for some reason. Yeah, nature doesn't always choose the prettiest things, so this is just our preference.
Well, let's thank our speaker again.
Yeah. Like this is an interesting lecture hall here with space.
Yes, that's the like,
I feel like I realized that I sort of like pinned myself in.
yeah, but you can also just, you can do one of these.
Yes, I wasn't sure if I was
Yeah,
adding that
just
back on.
don't try to lean back. Yeah.
I didn't forget.
Steve like the Maxwell.
Right, I mean,
I have to take off, but
It's
thank you
good
for
seeing
coming. It's
you.
nice seeing you. I'm sure we'll be in touch.
I'm like, we'll be in touch and you have a mission
Yeah.
for Matt.
All right, have a great trip.
Excellent, thank you.
Very nice talk.
Oh, thank you. I'm glad you enjoyed it. Oh, excellent.